Hey everybody, and welcome back to Patel Academy. Today I wanted to go over the 2018 AP Physics C Mechanics free response questions to give you guys an idea on some of the common types of questions that could come up on the AP exam, as well as talk about some of the common concepts and some of the errors that students may have faced in terms of interpretation or answering the question, especially because now the exams are moving towards more conceptual questions and theoretical questions rather than just calculations, especially for physics. Now I will try and make this a timed walkthrough, so I'll try and follow the timing guidelines put into place by College Board for this exam. But if I go a little bit above, it's because I'm explaining some of the concepts, and so I might go a little bit above the time limit. But when you guys write your exams, because you're just going to be doing the questions, if you have a thorough understanding of the concepts that you will get by watching my videos, you guys will definitely be able to finish the questions in time. So let's get right into it for AP Physics C Mechanics with question number 1. So a student wants to determine the value of acceleration due to gravity for a specific location and sets up the following experiment. A solid sphere is held vertically a distance h above a pad by an electromagnet, and so the electromagnet will turn off, the sphere is released, and we essentially measure with a timer the total time taken to fall this distance h, and from that we can determine the value of gravity. So what it says, while taking the first data point, the student notices that the electromagnet actually releases the sphere after the timer begins. So would the value of g calculated from this one measurement be greater than, less than, or equal to the actual value of g at the student's location? Okay. So for 1a, one of the conceptual things that you needed to notice here is that if the electromagnet releases it after the timer begins, there's going to be a small portion of time where the timer is still running, but there's no actual acceleration on the sphere. It's still at rest because the electromagnet is still holding it up. And so the total time, so I'll write measured time as Tm, is greater than the expected time, Te. So our measured time is greater than the expected time. Because of that, we're going to have a greater total amount of time. And so if you recall our kinematics expression for freefall, delta H, or in this case, delta H is equal to V naught T plus 1/2 AT squared. And so our V naught T portion, this gets canceled out because we're at rest initially. And so what we see over here is that there's acceleration. Acceleration is proportional to 1 over t squared. Right? So acceleration is inversely proportional to t squared, or is directly proportional to 1 over t squared. And so because our time total increases, the acceleration will decrease because it's an inverse relationship. And so the correct answer here is less than. And so you can kind of explain this just by words as well without the proportionality relationship, that, well, if you travel a distance in more time, then clearly you have less speed and less velocity and less change in velocity, and thus a lower acceleration compared to what's expected. That was 1a. For 1b, so the electromagnet is replaced so that the timer begins when the sphere is released, so we've corrected for that error. The student varies the distance h, and the student measures and records the time delta t of the fall for each particular height. So we're given the data table. Indicate below which quantity should be graphed to yield a straight line whose slope could be used to calculate a numerical value for g. Okay. So one of the things that we have to consider now is that I'm going to use this kinematics equation again, right? So delta H is equal to, now we have 1/2 A, and instead of T, I'm going to write delta T because that's what we are given, squared. And so if you notice, when I rearrange, if I plot delta H over delta T squared, I get A over 2, so I get the acceleration divided by 2, but in this case, our only form of acceleration is through gravity, so I can rewrite this as g over 2. And so g over 2 will be the slope of a plot between delta H and delta T squared, and then we're just going to have to account for the half when we calculate our actual value of g later on. And so for this question, our vertical axis, VA, should be height, and our horizontal axis should be delta t squared. That's one of the things to notice when you're talking about these kind of graphical questions, is how exactly do I set up my graph? You just have to rearrange the problem in order to get some sort of value on top and on bottom to represent a slope. So in this case, I had delta h over delta t squared. And so that represents essentially my slope, delta y over delta x. So I just need to plug in the corresponding y and x into my vertical and horizontal, my corresponding x and y into my vertical and horizontal axes to be able to figure out exactly what my slope is going to be. Alright, so that was part B. And so part C asks us to actually plot the data. So first of all, I'm going to utilize the table in order to calculate my essential values, and then I'll do a quick plot on the side. So our table has h, delta t, and now I'm going to add another column, delta t squared. So this is really messy. So I have 0.1, 0.2, 0.6, 0.8, I'll just add another column, 1. So I have 0.105, 0.213, 0.342, 0.401, and 0.451. Oops. Sorry, that's really messy, but you know the values. And then just using a calculator in order to get all these squared values. So this first one is going to be 0.011. Second one is going to be 0.045. Third one is going to be 0.117. This next one is going to be 0.161. And then this last one is going to be 0.203. Okay, and then we can create a rough sketch of the graph. So approximately, remember, for a vertical axis, we decided to do height. And then for a horizontal axis, we decided to do delta t squared. And so keep in mind, the question clearly says scale and label all axes, including units if appropriate, and then draw a straight line that best represents the data. So first of all, this will be delta t squared, and the units are going to be second squared. This axis is going to be height. It's going to be in meters. That was given in the question and in the data table. And then for an approximate scale, I see that my delta t goes up essentially to 0.203, so I'm going to keep it 0.205. So I'll label it as and then for my height, I essentially go to 1. So because we're given 5 grids essentially on this graph, I'll go up by 0.2. Okay, and then to draw an approximate graph, at 0.105 we have 0.1, so it's about here. Then we have it was 0.01. I read that wrong. And then we have 0.045, so just a little bit before 0.05, and we have 0.2-ish. Then we have 0.117 and up to 0.342, so just a little bit before, or sorry, that's 0.6. So just a little bit after 0.1, I go up to 0.6. The next one is 0.161, so a little bit after 0.15, and it's 0.8 as the height. So about here. Oh, actually, let me erase this other one. And then 0.203, so a little bit after 0.2, and I go up all the way to 1. So you can see it's a fairly straight line. It would definitely be more accurate on when you're actually doing it on the grid paper, but because I'm doing it without any grid lines, just a quick sketch, it's going to be fairly inaccurate, but that's an approximate line of best fit. Now, important to keep in mind when you are drawing your lines of best fit, here we're given 5 data points, so you should try and aim for 2 above the line and 2 below the line, or 1 above the line, 1 below the line, and then the rest on the line. So that should be approximately what you're aiming for to get the best results. Usually you won't have everything on the line, so you aim for 2 above and 2 below, and 1 on the line. Okay, so I believe we did all the points. We labeled the axes, scaled the axes, included our units, and then drew a straight line. Okay, so moving on for part D. It says, using the straight line, calculate an experimental value for G. Okay. So if you remember our equation over here, we said that delta H over delta T squared, which is a slope, is equal to G over 2. And so remember that we would need to multiply the slope that we get by 2 in order to get our actual value of G. And so G is equal to 2 times our slope, which is equal to 2 times. So for delta H values, if we want, we can go over here and pick our best values. You would do this off of the line of best fit. Now, for my purposes, because I don't have the exact values, but I know when I were to draw, if I were to draw this on the actual grid line, by inspection, there are a couple of points that look fairly nice to use. So one of them was 0.8 and 0.16 or 161. So very small range over there. And the second one would be around 0.2 and 0.04, sorry, were the points that I would use. Now you can use any other points as long as it lies on the line and you know that it's easy to work with. These are just the ones that I found would be the best to utilize. So my slope would become 0.8 minus 0.2 over 0.16 minus 0.04. And so based on these points, I can calculate my value of G to be 2 times, this would turn out to be 0.6 over 0.12, which is equivalent to 2 times 5, which is equal to 10. So I believe that they accept fairly wide range of answers. Now, of course, over here, I'm just using estimates based on my line of fit and based on what I did on this problem, but you usually, for the denominator, would go to 3 decimal points, and that would get you the precise accuracy to get something within the interval of 9.9 and 10. And I believe any of these values are acceptable as long as you clearly show that you chose a point off of your line. Now, if you did an actual linear regression for this, which if you do know how to do, it can help to get precise answers based on the data points, but then the value you would get would be 9.66. And then keep in mind, so for my purposes right now, I got 10, so I would go 10 meters per second squared. Remember to include those units. And so, as you might know, on the AP Physics exam, we are allowed to use the estimation of G is equal to 10 rather than 9.8 or 9.9. So, because of that, an answer of 10 is a little bit overestimating, but it is still a reasonable answer. It's not something like 20, in which case you know that you've made a mistake. Okay, part E, section I. So another student fits the data in the table to a quadratic equation, at squared plus bt plus c. Vertically down is the positive direction in this case. Using the student's equation above, do the following. Derive an expression for the velocity of the sphere as a function of time. Okay. So this is often where there's a couple of free points. So whenever you see like part 1, part 2, part 3, and part 4, usually it's fairly straightforward problems that can allow for very quick points. And so for this first one, all I'm going to do is I'm going to plug in, I'm going to substitute this value into the kinematics equation that we covered earlier. And so the kinematics equation that we covered was delta H is equal to V naught T plus 1/2 AT squared. So delta H is equal to V naught T plus 1/2 AT squared. Except what you can do now is our delta H is going to be Y. So it's going to be Y2 minus Y1. V naught T plus 1/2 AT squared. And so I can write, I should write Y minus Y naught. That's the traditional way of writing this. So I should say Y minus Y naught. And so I can rearrange to get Y is equal to Y naught plus V naught T plus 1/2 AT squared. And I believe this last formula is one they actually give it on your formula sheet. So if you didn't want to do this work, you could just directly take that off of the formula sheet. Now if you notice, I'll outline this in orange. This equation that we got is a quadratic equation. And so this is a common trick that we use in math, but oftentimes what you can do is when you're given a polynomial to a certain degree, you can match the coefficients of the like terms, of terms with the same degree. And so we know that because the distance y has to be the same, so we know that y naught plus v naught t plus 1/2 AT squared has to be equal to the quadratic fit given AT squared plus BT plus C. And so now what we can do is we can match our coefficients. So the velocity of the sphere as a function of time is going to be we can figure out the initial velocity. Now we know that the velocity is just the derivative. And so the derivative of this expression would become, with respect to time, would become V naught plus AT. And then again, taking the derivative of the other side, we would get 2 capital AT plus B. And so you can either leave it as just this expression, or you can plug in the actual values, and you would get 11.5 T minus 0.524. And then keep in mind this would be in meters per second. Okay, so for this problem, if you recognize that you could just take the derivative, it's not a problem. It makes it much easier. The reason why I did these initial steps is because they should help. The matching the coefficients is a problem solving strategy that you guys should know how to do, and it will help in future parts. So for part 2, for example, we're asked to calculate the new experimental value of G. So what we can do is, using this derivation that we got, y naught plus v naught t plus 1/2 AT squared is equal to capital AT squared plus capital BT plus C, we can compare the coefficients where G is. And so what we notice is that A, our capital A, corresponds with 1/2 lowercase a. And as I said earlier, the only acceleration we have is G. And so what we can see over here is that because we've matched the coefficients, so in front of the t squared, there's an a on one side, in front of the t squared, there's a 1/2 lowercase a on the other side. So I can just say that G is equal to 2a, which is equal to 11.5 meters per second squared. So that's the experimental value. Now for part 3, as you may have wondered while you were doing this question why you got such an absurd result from this quadratic fit, it says calculate the percent error for the value found in part E, part 2. And so one of the things is that people often forget the percent error formula, and so keep in mind that percent error is equal to the absolute value of the actual minus the experimental so actual being the theoretical value, and then divided by the actual. Or sorry, it should be actual and then it should be accepted and experimental. It just depends on what formula you choose. And so one of the things to notice is that on the top, because of the absolute value, or sorry, I should probably write times 100 as well. So one of the things to notice is that on the top, because it's absolute value, it doesn't matter the order that you do your subtraction in, it just matters what you're dividing by. And so just note that you're dividing by 9.81 in this case. And so I just get 9.81 minus 11.5 divided by 9.81 times 100. So plugging that into my calculator, I get 17.2%. Okay, so the experiment had an error of 17.2% when calculating the value of gravity, of the gravitational acceleration. And then finally, part 4 of this, assuming the sphere is at a height of 1.4 meters at time t equals 0, calculate the velocity of the sphere just before it strikes the pad. Okay, so this one, again, we can use kinematics for this. And so we know already that our acceleration is equal to 2a, which was equal to 11.5. We also know that our y naught is equal to c, which is equal to 0.08 meters. This is meters per second squared. And so what we can do is we can utilize a kinematics equation. V squared is equal to v naught squared plus 2a delta y. So this is another equation that's given on the formula sheet. And so we can just solve. So v is equal to the square root of v naught squared plus 2a delta y, which is equal to the square root of our v naught. What we also know is that, I'll write this over here, I forgot to, v naught as according to the equation is b, so it's just negative 0.524 meters per second. And so we get negative 0.524 squared plus 2 times 11.5 times now we're given that the sphere originally is at a height of 1.4 meters, and then our y naught is 0.08. So our delta y would just be 1.4 minus 0.08. And so you can do this entire thing on your calculator, and you should get something around 5, I believe. But it's 0.524 squared plus 2 times 11.5 times 1.32 square root. I get 5.5348, which I can round to 5.53 in this case, or 5.54. Meters per second. So both of these values would be accepted. Okay. One of the other ways that you could do this was simply to solve for your t and then find out the velocity at that final time t. So you can find the total time it takes for you to drop this distance, 1.4 minus 0.08, and then you can figure out the velocity at that final time, which is just before it strikes the pad. And that marks question number 1. So let's move on to question number 2. Keep in mind this is one of the shorter exams because it only has 3 questions, albeit them being kind of long. So there's usually almost always a rotational question at the end, and then usually the first question is heavily focused on kinematics, and the second question is heavily focused usually on dynamics and things like work or impulse or power, so those middle units. And then occasionally you might have something like simple harmonic motion or Hooke's law or something like that thrown in. So question 2 says 2 carts are on a horizontal level track of negligible friction. Okay, cart 1 has a sensor that measures the force exerted on it during a collision with cart 2, which is at rest. Alright, the total mass is 0.5 kilograms of cart 1 and the sensor. Mass of cart 2 is 1.05. Spring has negligible mass, that's usually what we assume. The spring has a spring constant, K is equal to 130 newtons per meter. And we're given a graph for the force with respect to time, and we're given a quadratic fit equation, F is equal to 3200 t squared minus 500 t. So part A says, using integral calculus, calculate the total impulse delivered to cart 1 during the force. Okay, so this one is a fairly simple question because it's just a formula that you can use. So we know that our impulse, J, is equal to the integral of F with respect to time. And so we're essentially just going to take the integral, and our bounds are going to be the total time. So from time 0 to time 0.16, which is essentially where we have our data range. So from 0 to 0.16, we take the integral of 3200 t squared minus 500 t with respect to time. And so this is just a simple polynomial integration. Oh, why am I writing the integral sign again? I can just directly solve this. And so we get 3200 over 3 t squared, t cubed, sorry, minus 250 t squared, and then all evaluated from 0 to 0.16. And so when we plug this in, when we put in 0, you're just going to get 0, so all you have to do is plug in 0.16 in this case, and you get negative 2.03. And so keep in mind, if you didn't know the units directly of impulse, you can actually use the integral in order to figure out. We're taking the integral of force, which is newtons, and then this is with respect to time, so the dt contributes seconds, because dt essentially is just a minuscule amount of time. So it's an infinitesimally small amount of time, but it still has unit seconds. So the integral of force times time is just the integral of newton seconds, which is just newton seconds. So in this case, you can think about it as you're adding on the seconds to your newtons. And so one of the things to also consider, if you didn't necessarily know, is we can consider it based on the units of the coefficients given as well, or of course you can just memorize the units for impulse. I would personally strongly recommend you memorize the important units for all of the major quantities so that you wouldn't have to derive and think about which unit makes sense on the spot. But there are definitely ways to think about it if you do forget. Okay, so B part I says calculate the speed of cart 1 after the collision. Okay, so I'm going to actually do this on another slide just so I have space, because we are going to be using, as we do in most collisions, conservation of momentum. Okay, so calculate the speed of cart 1 after the collision. We have, actually in this case, I'm going to make it a little bit simpler, because what I know is that the impulse is equal to the integral of f dt, but it's also equal to the change in momentum. And so what I can say is that my impulse, which you just calculated, is equal to our mass, which stays uniform for cart 1, times V1 final. I can say, I was going to say V2 minus V1, but it's probably easier to distinguish cart 1 and cart 2 by writing V1 final and V1 initial, So the mass of cart 1 that we're given is 0.5. We just found this was negative 2.03. Right, yeah, negative 2.03. And then our V1 final is what we're looking for, and our V1 initial is, so I'm just going to indicate this as V1. V1 final, and then minus our initial, which is 3. Okay, and then so what we see is that V1 final is equal to negative 2.03 divided by 0.5 plus 3, which is equal to, I'm dividing by 0.5, so multiplying by 2, so I get negative 4.06 plus 3, which is negative 1.06 meters per second. And so while this isn't always necessarily true, if you think about the force and the restoring force of the spring, it makes sense that the cart would press in the positive direction against the spring, propel the cart forward, and then also get a restoring force that pushes it backwards. And that's why it makes sense that our velocity is negative. So it's traveling in the opposite direction from what it was initially. Okay, so part B, double I, is essentially just, and then the proper interpretation of what I just said. So in what direction does cart 1 move after the collision? Left, right, or the direction is undefined? Well, because it's negative and we chose 3 to be our positive value, we know that it is left. So no justification for that question because it's a fairly straightforward question. Okay, calculate the speed of cart 2 after the collision. Now, this one is where, once again, you could just use the, you could use conservation of momentum, or you could once again use a slight shortcut. So we know that m1 v1 plus m2 v2 initial is equal to m1 v1 plus m2 v2 final, right? Now what we know is that m2 v2 initial is 0. And so what I can say is that m2 v2 final is equal to m1 v1 initial minus m1 v1 final, which is equal to, I'm going to factor my m1, so v1 initial minus v1 final, which is equal to the negative m1 v1 final minus v1 initial, right? So this is just factoring it out a negative 1. And so we know that m1 times the v1 final minus v1 initial, so m times delta v is delta p. So this is just our impulse that we calculated, except now it's negative impulse because of the negative sign in front. And so what we know is that v2 final is equal to negative impulse over m2, which is equal to 2.03 divided by the mass that we were given of 1.05. And so we can just calculate that. And so that's one of the ways that you can interpret the conservation of momentum in a way where you don't have to plug in all the values. You can use a little bit of simplification to just get the expression negative impulse over mass. So we get 1.93 meters per second. And so now we're told in part 2 that show that the collision between the two carts is elastic. Okay, well, we know that momentum is always conserved, but to show that it is an elastic collision, this is a little tangent, we need to have conservation of momentum and kinetic energy. And so how exactly do we do that? Well, we just have to show that the initial, so K1 plus K2 initial is equal to K1 plus K2 final. Okay, and so once again, we know that because cart 2 is at rest, this goes to 0. And so we're essentially just left with 1/2 mv squared. So 1/2 m1 v1 initial squared is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And so now that we've gone through part B and C, we have all of the things we need, all of the numbers we need. To calculate this, which is 1/2 times 0.5 times 3 squared, which is equal to 1/2 times 0.5 times negative 1.06 squared plus 1/2 times 1.05 times 1.93 squared. And so on this side, we get 4.5, 2.25 joules. And on this side, putting that into my calculator, I get 2.24. And so this is close enough to where we can say that because they're approximately equal, kinetic energy is conserved. And so because kinetic energy is conserved, I'll rewrite that, that looks really messy. Collision is elastic. Okay, part D now. So it says calculate the speed of the center of mass of the two-cart spring system. So the center of the mass between the carts and the spring. Okay, so what we know is that even with this, so the center of mass, we have to consider, we can use the formula, or we can just consider conservation of momentum again, but this time solely in terms of the center of mass of the two-cart system. And so what we have is M1, sorry, I should write 1 as a subscript. So M1 V1 initial. I'll write this again just for completion. Is equal to, now we want to find the speed of the two-cart spring system. So now we can combine. So we get M1 plus M2 times V center of mass, which would end up being the final. Okay, once again, we know that this one goes to 0. And so what we have is that the velocity of the center of mass, so or the speed of the center of mass in this case, is equal to M1 V1 initial divided by M1 plus M2. So if you guys don't know how exactly I got this equation, it's because initially we can consider the carts separate because the two-cart spring system essentially comes together during the collision. So that's why we use conservation of momentum. And so the reason why is because initially we have them separate. If you wanted to consider at the start as the center of mass, you could, because one of the things is stationary, our V center of mass initial is just going to be our V1. But because we don't want to consider the mass of the second cart initially, only afterwards, we write it like this. So it's M1 V1, which is the total momentum initially of the system, is equal to the system together, m1 plus m2, because that's when they interact, times our total velocity of the center of mass. And so this one we can easily figure out. So the top would just be 3 times 1/2, which is 1.5. Bottom would be 1.55. So we have 1.5 divided by 1.55, which is equal to about 0.97. So our speed would be 0.97 meters per second. If you guys don't understand exactly how we can utilize these equations in terms of the center of mass like I did over here, one of the things you can do is visualize that we only really consider the center of mass for collisions like this when the two objects actually meet or interact with each other. And the second thing is that I highly advise you guys go and review not only how you calculate the center of mass, those formulas, but also how exactly you use center of mass in different applications. So you can have the acceleration or velocity or position of a center of mass, but at the same time you can also have other applications in terms of rotational motion or in terms of things like impulse and gravity of the center of mass of an overall system. So that was part 1. Now part 2 says calculate the maximum elastic potential energy stored in the spring. Okay, so for this purpose, I personally prefer using just conservation of energy. I think it's probably the fastest method, but what you could do is you could calculate potential energy as the derivative of force. You're given the information for force within the question, and then you can figure out what exactly the maximum elastic potential energy is, because by Hooke's law, F is equal to negative kx. So you're given the force, you're given k, you can calculate x max, and then from x max you can calculate u max. The way that I like to go about this is by using conservation of energy to calculate directly the potential energy stored in the spring. So my k initial is equal to k final. So I write, once again for completion's sake, k initial plus u initial is equal to k final plus u final. Now in this case, because as you can see the relative positions, so our frame of reference, if we consider the ground, then the relative position of the spring before and after, as well as the kinetic energy of the cart and spring system as a whole, it's all going to be constant within the frame of reference. And so that's why I don't need to consider the potential energy from gravity or from position. So I just need to consider potential energy of the spring, so by Hooke's law. And so what I can do is switch to orange. I can set this equal to 0 because our spring initially isn't compressed, and so there's no potential energy being stored. And then I can rewrite this as k initial is equal to k final of the system plus u of just the spring. So we don't need to consider the potential energy from gravity. And so once again, we have 1/2 mvi squared is equal to 1/2 mvf squared plus 1/2 I'll just write plus us because that's what we're solving for, so I don't need to plug in 1/2 kx squared for that. And so us becomes 1/2 mv initial squared minus 1/2. Now in this case, our mv squared, we're going to use the center of mass of the entire system. So the reason why we went about the speed of the center of mass of the two-cart system is so that in this case we can consider it as the system as a whole. So we have m1 plus m2 times v center of mass squared. And so we can easily just plug in. So once again, similar to the previous question, we're solving for v center of mass, so our v initial is just going to be 3. So we have 3 squared, which is 9, and then times 0.5 times 1/2, so 9/4, which is 2.25. Minus, this is 1/2, 0.5 times 1.55 times 0.97 squared, which is 0.73 approximately, and so this finally turns out to be 1.52. And then our potential energy is in joules. So keep in mind that when we're considering problems like this, where we're trying to find the potential energy stored in the spring, we have to consider the system as a whole, and that's why I have the m1 plus m2 and then the v of center of mass squared, rather than just of an individual part, as we may have used in part B and C. Okay, so that marks question 2, and now we're on to question 3, a rotational motion and rotational dynamics question. So a triangular rod shown above has length L, mass m, and a non-uniform linear mass density given by the equation lambda is equal to 2m over L squared x, where x is the distance from one end of the rod. And so we're given in the diagram that we consider the pointy part or the sharp aspect of the rod to be x is equal to 0, and we can move up the rod until we get x is equal to L. So we're given a non-uniform linear mass density, and the first question is, using integral calculus, show that the rotational inertia of the rod about its left end, so about the point x is equal to 0, is just ml squared over 2. Okay, so this topic particularly is one that students often gloss over, and so it was a cause of a lot of problems for students when they were writing this test, because people often just remember inertia in terms of its applications for torque, in terms of torque is equal to the inertia times the angular acceleration, or in terms of kinetic energy, rotational kinetic energy, sorry, but they often forget how exactly you can derive, using integral calculus, the rotational inertia. And so this particular formula is one that people often forgot. So the rotational inertia is equal to the integral of r squared dm. Now what exactly is dm? Well, dm is a very small section of mass. And so what we can do is we can relate our non-uniform density with regards to mass. And so if you think about it, I'll just draw a little squiggly line over here. What exactly is density? And how exactly can we relate density to mass? Well, density is essentially, or I guess the direct formula that you can use is mass is equal to the integral of density dx. This is a formula that we've seen oftentimes, not only for rotational inertia purposes, but also for center of mass purposes when we're trying to calculate our actual mass and we have a non-uniform linear mass density. And so what we can do is we can rewrite this integral by plugging in the information. So we have 2m over L squared times x dx. And so our dm is equal to lambda dx is equal to 2m over L squared x dx. So this might seem a little bit counterintuitive, because you might think, oh, well, you could have just written the second expression. The reason why is because, so this first expression is the definition of mass with respect to density. So it's essentially the accumulation of density over a distance that gets you the total mass. Or you can think about it as weighted mass, for example. So when I plug in, and when I take the derivative, so essentially the derivative of m becomes dm. So I'm taking a minuscule amount and I'm trying to find how exactly that minuscule amount of mass changes. We can use the fundamental theorem of calculus, if you know what that is, to essentially the derivative cancels out the integral in this case. And so we are just left with dm is equal to lambda dx. But if you think about it conceptually as well, you can go directly to the second point. So if I have let's say if I have a shape, and I take a very small section dm with width dx, then I can say that my density is going to be equal to dm over dx. So it's going to be equal to mass over that small section. And so, or I guess in this case, if I took a small section, it would be dA. So it's a minuscule area, but if it was like a uniform rod, let's say, and I took a small section of the rod, then I get the mass over this distance, the minuscule amount of mass over the minuscule amount of distance gets me my density. And so from there we can derive that dm is equal to lambda dx. So that's just a little bit of a tangent if you wanted to know how exactly that gets derived, but more complete and complex derivations you can easily find elsewhere. So what we know is that our dm is going to be 2m over L squared times x dx. So then we can go back to I is equal to the integral of r squared. Now what exactly is r? So when we want to plug into this integral, we get our dm. I'll write that out as so our radius in this case would be x, and so we can rewrite this as our dm being 2m over L squared times x, and then we also have times x squared, and then we have a dx. So the reason why I can rewrite this above as this is the integral of x squared dm. So in this case, our radius, as you can probably see in the figure below, figure 1 and figure 2, our radius is going to be x. Okay, and so this is not a fairly hard integral to evaluate. So keep in mind we're going to be integrating, because we're integrating with respect to x, we have to consider our bounds as well. So we're going to be integrating from the bounds x is equal to 0 to x is equal to L. Those are the two boundaries that were given in the initial figure of the problem. And so I'll just rewrite this as from 0 to L of 2m over L squared times x cubed dx. Now m is a constant, L is a constant. You can rewrite this as 2m over L squared times, this will turn into x to the 4th over 4 evaluated from 0 to L. At 0, this entire thing will turn to 0. At L, I get 2m over L squared times L to the 4th over 4. So L to the 4th divided by L squared is just L squared. So I get m L squared, and then I have 2 over 4, so divided by 2. And so that's exactly what we needed to show. So this was a tricky problem in the sense that you needed to know this initial equation that people often forget. You also needed to know the relationship between mass, density, and distance. And then you needed to apply your integration to get this proof that it's ml squared over 2. Okay, for part B, it says derive an expression for the rotational inertia I total of the hoop rod system about the center of the loop. So we have a hoop with mass m, radius L, and a rotational inertia about the center of ml squared. We also have 3 rods, which are identical to the ones that we found earlier. So they'll have the same mass, radius, and rotational inertia. The rotational inertia being the one that we found in part A as being ml squared. And keep in mind that that's about the left end of the rod, and if you look in the picture, the left end will be in the center, so they'll coincide perfectly, and so that should be a hint. So we're trying to find the total inertia about the center of the loop. Okay. So this is also one of the things that people may have tried to overcomplicate, but actually inertia is a summable quantity. So we essentially, so our I total is equal to, well, we have 3 rods, and we have 1 hoop. So this is just 3 times ml squared over 2 plus ml squared. So you can just work at the math to get 5 ml squared over 2. So a very giveaway question, as long as you realize that you could actually add the rotational inertias together in order to get your final answer. And it says the hoop rod system is initially at rest and held in place, but is free to rotate about its center. A constant force, F, is exerted tangent to the loop for a time delta t. Derive an expression for the final angular speed, omega, of the hoop rod system, and express your answer in terms of m, l, f, delta t, and physical constants as appropriate. Okay. So how exactly can we go about doing this? Well, we are given that there is a force exerted tangent to the hoop for a time delta t. So what we should know initially is that there is going to be a torque. What we can also deduce is that we can relate our torque, our time, our inertia that we're given, and our change in angular speed. And so what you may know is that because there's a torque, our torque times delta t is equal to I delta omega. So you can derive this expression, and then you get I omega 2 minus omega 1. And so what exactly is our tau? Well, our tau is just FR. So it's just FR, and then we have delta t. That looks like an E. It's supposed to be an F, so I'll fix that. Why? Well, because keep in mind that torque is equal to R cross F. So the magnitude is going to be the magnitude of R times the magnitude of F, and then times sine theta. But in this case, it is tangent to the hoop, so theta is 90 degrees. Because theta is 90 degrees, sine of theta is 1, and so our magnitude of the torque is just F times R, and we can further simplify this as R is equal to L, as we're given, I believe we were given at least. Or you can interpret that as well as we've done in previous questions. So it wasn't explicitly stated, but you can, and so we know that F L delta T is equal to I. Now our I was 5 over 2 ml squared, and then our omega 2 was just, our omega 2 is what we're finding because that's the final, and our omega 1 was 0 because our system was at rest initially. So I just have omega 2. And so we can solve for omega 2 as being, when I divide, I get 2 F delta T over 5 ml. Because, yeah, the L and then the L squared will cancel. Alright. So that is the answer for the final angular speed of the hoops rod system. Okay, so part D. So our system is rolling without slipping on a level horizontal surface with the angular speed found in part C. So we rotated it a whole bunch, we got an angular speed, and then we let it roll without slipping along this horizontal surface. At time t equals 0, the system begins rolling without slipping up a ramp. So part 1 says, on the figure of the hoop rod system below, draw and label the forces, not their components, that act on the system. Each force must be represented by a distinct arrow starting at and pointing away from the point at which the force is exerted on the system. So in this case, you probably have seen rolling without slipping questions. So in terms of forces, there's only 3 of them. So I will try and redraw this in blue. So we have our circle, we have our rods, and then we have our line, our ramp. Sorry, it should be touching, I'll redraw it. Yeah, so essentially like that. And so the forces, I'll draw in orange. So the different forces that we have in terms of rolling and slipping are the normal force, the gravitational force, and the frictional force. And so when we're rolling without friction, without slipping, the frictional force is often the one that provides the torque. So the normal force occurs from the surface going through the center. And we'll try and redraw that since my hand slipped. So that is the force of the normal. So it goes to the center of mass originates from the surface acting on the system. We also have a force of gravity that originates at the center of mass and goes straight down. Sorry for the squiggle. And then at this point of contact, we have a force of friction as well. Whether you indicate it with just a lowercase f or whether you indicate it like me with capital F and then subscript lowercase f, those are the two systems. And so what we also need to consider over here is that the direction. And so, of course, the force of gravity and the force of normal are going to be in the direction specified, but the force of friction is actually pointing, in this case, in the direction of motion. So that's important to consider. It is pointing in the direction of motion, in this case, because we're going up the ramp. So part 2 is essentially that question that I just posed. Didn't realize that, but it says justify your answer in terms of your directions. So number 1, normal force Fn always perpendicular. To the surface and pointing away. And so because of that, it's going to be upwards and to left. So I like to be, for questions like this, I like to be very specific. So I clearly said upwards and to the left, but I'm not sure. You can probably just say that it's going to be perpendicular to the surface and pointing away from the surface, and you should still get full marks. I'm just not sure. For number 2, the gravitational force. He's almost down. From the center of mass. And then number 3, frictional force. So it's always opposite. Now in this case, because we're considering rolling without slipping, unlike your traditional motion where it's simply opposed to the direction of motion in general, it has to be, in this case, always opposite to the direction of rotation. And so while our motion may be up the ramp, our rotation in this case is actually counterclockwise. And so because our rotation is in this manner, our frictional force has to be opposite to that. Or sorry, I drew this the wrong way. But our frictional force has to be opposite the direction of rotation. And so if our frictional force is like this, it has to be opposite to our direction of rotation, which has to be in this direction. So yeah, I did draw it right. So I can write, and so it must be pointed up the incline. So yeah, if you didn't understand specifically the frictional force thing, don't worry, a lot of students did mess this up. Specifically, they often put it down the ramp because traditionally, when you're considering an object that, let's say if you applied a force and it's now moving up the ramp, then the frictional force would be directed down the ramp initially. But it's important to consider that in this case, because we're talking about rolling without slipping, the frictional force is opposite to the direction of rotation, not necessarily the direction of translation. So I would recommend you guys review some of the examples involving this if you didn't fully understand that. And then for question E, which I believe is the last question, yep, it says derive an expression for the change in the height of the center of the loop from the moment it reaches the bottom of the ramp until the moment it reaches its maximum height. Okay, oftentimes this is similar to your normal translational motion where we're trying to find the height, and so because we have a changing height, we can just use conservation of energy. It's often the case in rolling without slipping problems as well that we just use conservation of energy. And so our K1 plus U2. Now, what we know is that at the start, we're at the ground, and then at its max height, we have none of this. So K1 is equal to U2. Now, what we have to consider is that our K1, so the kinetic energy at the bottom of the ramp, we have, as we see in rolling without slipping problems, we have a translational, squared, plus we have our rotational. And then in terms of this, our U2 is just going to be mg, and then our height, I'm going to use h. Unless if, yeah, I can just use h because it doesn't specify whether we need capital or lowercase or something like that. So we have this, and so I'll just rewrite that just so that I can work through the algebra and you guys can see the steps clearly. So then my h is equal to 1/2 squared plus 1/2 I omega squared over mg, which is equal to, now what we have to consider is our, in rolling without slipping problems, our v is equal to r omega, right? So this is our conversion between our rotational and our translational systems. And so in this case, L is equal to R, as we've seen multiple times in other questions. And so V is equal to L omega. Now, one of the things that you guys can recognize on why exactly we do this is because in the question, this is express your answer in terms of M, L, I total, and omega, and physical constants as appropriate. So nowhere is V listed in that case. So because of that, you would get a sense of what type of conversions you'd have to make. So we know that our mass will become capital M. We know that our I will become I total, so that's fine. G is a physical constant, so you know exactly which terms you have to convert into maybe a different analog or an equivalent expression in order to get it solely in terms of the quantities that they've listed. So that is a good way for you to figure out what exactly you need to substitute and when. So I get 1/2, this time this would be capital M. So I'll leave it M for now, but I will convert it to capital M afterwards. And then this is L omega squared plus 1/2 I omega squared over mg. So this is equal to, I'm going to factor out a 1/2. I'm going to get an m total. Now this will play into part because we haven't had to work with this before, but keep in mind that this is the object in consideration is a hoop with the 3 different rings or rods within it. We're given that the hoop has a mass m, and we're given that each of the rods has a mass m, and so our total mass is going to be 4m. So I have m total L squared plus I, this is I total now, and then I'll also factor out an omega squared, and then still divided by, this is now m total g. So my m total is 4m, so we have 4m L squared plus I total, this is all times omega squared, over, this is 4m times g, and then I'm going to bring this 1/2 down, so it becomes emg. And so I believe that is the simplest answer that we can give, unless you were to split the fractions, but I think they want everything to be together. If you were to split the fractions, then you would get something like L squared over 2g plus I total, sorry, you get L squared omega squared. Plus I total omega squared over 8mg. So whichever one is more simple to you, they're both equivalent expressions. So yeah. And that marks the end of the 2018 Physics C Mechanics problems. If you have any specific questions, feel free to leave them down in the comments below and I'll reply and explain any concepts or things that were unclear. There were quite a few in this one. So there was the frictional force and its direction. The other ones were the center of mass and why exactly we use the center of mass when we're calculating our potential energy. So there were a couple of oddballs, especially this integral calculus one that quite a lot of people forgot. So I'd highly suggest you review that and review those specific small things that you might think never come up, but sometimes they did. And in quite a few of these questions, if you didn't get that first one, if you didn't know that relationship, you wouldn't have been able to answer some of the other ones as well. Luckily, later on, they let you just do I total. But if they did want you to substitute for I total, as we found before, you might have lost more points. So remember to review those things. Thank you all so much for watching. I really appreciate all your support. Remember to like, comment, and subscribe. And hit that notification bell for my future videos. I'm planning to do a full AP Calculus and a full AP Physics and potentially a full AP Chemistry review for you guys to use just before your AP exam to get it refreshed on all the concepts. So let me know in the comments if you'd like that, and I'll see you guys next time, and good luck on your AP exams whenever they start up. Alright? I'll see you guys in the next Patel Academy video.